Hey, this is Group B23 from EECS 203 at the University of Michigan, and today we're going to be explaining to you guys permutations with indistinguishable objects. Alright, so let's start with a question. Imagine you have 4 children, Billy, Cindy, Jimmy, and Sally, and you want to pack their lunches. You have 2 apples, a banana, and an orange, and you're distributing them to one to each kid. How many different ways could you pack their lunches, given that you're going to be giving one fruit to each of them? Well, since we know a little bit about accounting thus far, we know this is going to be something to do with permutation, since we're worried about the order at which the fruit are going to be given, to whom they're going to be given in this case. So let's give the fruit labels, apple 1, apple 2, banana, and orange, and start to look at all the possible permutations. Well, our list is kind of long. We have 4 objects, so based on what we know about permutations thus far, we know that there's going to be 4 factorial or 24 different ways to change the order. But using this method, we assumed that because there are approximately 20 school days a month, and there are 24 different offerings, that we can give out fruit to our children for a whole month before having to repeat and give the same pattern over again. But one day during the first month of school, your kids come home and say, "We had the same fruit as yesterday, Mom or Dad." And the question that we have, and we have to scratch our heads, is what happened? Well, what we didn't take into account was this whole idea of indistinguishable objects. Indistinguishable objects are things that, in the context of the question, are identical. This is obviously in contrast to things that are distinguishable, and that's the way that we tried to count initially. We tried to force this into being a regular permutation. And in that case, you ask yourself, who has apple 1, who has apple 2, as though they're two separate events. So it's clear that, let's say this was Monday and this was Tuesday, and these are the 2 days that your kids came home and told you that they had the same fruit as the previous day. These are not equivalent when you're counting it this way, because there's obviously a difference. On day 1, Billy has apple 1, and on day 2, Billy has apple 2, so that's considered different. But if we were to treat the objects as being indistinguishable, instead of asking who has apple 1 and who has apple 2, we ask just the general question, who has the apples? And so in this circumstance, it's obvious that the same ordering as above is equivalent, because on Monday, Billy and Cindy have apples, and on Tuesday, Billy and Cindy have apples. It doesn't matter which apple they have. And so that's the main concept of indistinguishable objects. It's obvious that, common to both scenarios, if you were to flip 2 objects that were of different types, in this case we flipped the orange and the banana, then obviously that's not equivalent. So now let's quickly go through and count and see how this actually makes a difference. If we were talking about our regular permutations, like I said, we would start off by saying who has apple 1. And so let's just, for an example, give Cindy apple 1. Well, there were 4 spaces open, so there were 4 choose 1 ways to do that. If we say who has apple 2 as being a distinct and different event, let's say we give it to Sally, then there were 3 choose 1 because of the 3 remaining spots that were open before we placed it, and we're placing the 1 apple. Similarly, we continue who has the banana. Let's say we give it to Billy, and say we give Jimmy the orange. There were 2 choose 1 ways to place the banana, and 1 choose 1, or just 1 remaining way to place the orange, which gives us rise to the formula that we do know already, that the permutations of 4 objects in 4 spaces is just 4 factorial. But if the objects, we're now treating them as indistinguishable, the first event is just, again, who has the apples. So let's place both of the apples here. Let's say Billy and Sally have them in this case. There were 4 choose 2 ways of doing that. As opposed to up here, we had 4 choose 1 and 3 choose 1. We're taking care of we're killing 2 birds with 1 stone, so to speak. And then the other events, there would obviously be 2 choose 1 ways to place the banana, and 1 choose 1 ways of placing the orange. So that gives rise to our formula here. If we go through and do a little bit of work, we see that there's actually a very nice pattern of cancellation that occurs with the denominators and numerators and the 0 factorial term, which is actually obviously just equal to 1. And so we see that indeed we only have 12 ways of distributing these fruit as opposed to 24. So that explains why we didn't get through the whole 30 days or the whole 20 days of school that we thought we would. We only can get through 12. Obviously, there's going to be a repetition. Okay, so if we think about this in the general context, let's say we had n elements in total. There were m different types. And so let's say K1 elements were of type 1, like say apples. Say we had 2 apples. K2 of type 2, and so on, up to Km of type M. Clearly the sum of all of the objects is equal to n. If we follow the same technique that we did before, we place the first K1 elements, then we place the K2 until finally we place the remaining Km. Our equation is this. We start off with n elements. We choose the places for the K1, leaving us with n minus K1 places left when we place the elements of K2, and so on. And we see that very nice pattern of cancellation that we had before, where the denominator and numerator in succeeding terms, this and this denominator with this term, with the numerator in the following term, and the denominator in the previous term canceling with this term, and also 0 factorial, we get rid of that because it's just 1, and we're left with our very nice equation for the number of permutations with indistinguishable elements, where there are K1 of the first type, K2 of the second type, and so forth. However, what we should note is that this is the same. We should recognize the similarity between this and regular permutations, in that n factorial is the number of n permutations, and it's divided by the permutations of K1, permutations of K2, and so on. So why is that? Well, let's look at an example here. Let's say we had 3 green elements that are indistinguishable and 2 yellow objects that are indistinguishable. And if we just look at one of the permutations, i.e. green, green, yellow, and we were to label them as though they were distinguishable, i.e. we were counting it in the regular permutation method, let's look at let's break it apart into 2 different cases. First, we're going to fix the yellows, i.e. we're just going to look at the number of ways we can place, if we were to label these 3 green elements as 1, 2, 3, how many different ways we could place them such that they were in this form. And obviously, it's going to be equivalent to, it's simply going to be equivalent to the number of permutations of 3 elements, or 3 factorial. Similarly, if we were to look at the case where we're worrying about the yellow elements, there's obviously only 2 cases, but that's equivalent to the number of permutations of 2 elements, or 2 factorial. So what does this imply? Well, the greens, since they provide 3 factorial times more orderings than we want, and the yellows provide 2 factorial times more orderings than we want, obviously, if we were to count it in the regular permutation method, we would be overcounting by a factor of 3 factorial times 2 factorial, or the permutations of 3 times the permutations of 2. So therefore, if we were to use regular permutation and do it that way, we would need to divide by the number of permutations of the green elements times the number of permutations of the 2 elements, which is 10 in this case. But this leads us to our general equation that we covered just on the last slide, that the number of orderings is indeed equal to the number of total permutations divided by the number of ways, the product of the ways we can have permutations of the K1 indistinguishable elements. In this case, they were the 3 greens. K2, in this case, were the yellows, and so on, which gives us the same formula that we've been covering in the last couple slides. Alright, so here are 2 exercises. I'd encourage you to pause the video before looking at the solutions. Before I move on, I'm going to put links about here and here to the videos for the solutions. But the key concept that you should focus on, rather than, again, like I said, just jumping to the solution videos, is trying to recognize that these whole counting concepts that we're using are in fact very abstract. Counting seems like a very basic thing, like we're back in elementary school or something like that, and we're learning to count on the number line. But in reality, how many different ways can we rearrange the letters in EECS, or how many different paths can we take from the origin to some position in the XY plane, or even how many different ways can we give our children fruit for lunch, for that matter, all in fact rely on the same core concept. And so the focus of these two exercises and their corresponding videos is just that, this whole concept of abstraction. So before moving on, again, I'd recommend you try these exercises, but feel free to go back and watch the videos and the solutions as many times as you'd like. One key application that is very useful is the multinomial theorem. It's very similar to the binomial theorem, except in this example I have three terms, but it could be anything. It could be w plus x plus y plus z, or any number greater than 2, which of course is implied by bi in binomial. So if we're using x plus y plus z as an example, and we raise it to some power, what we need to first the most important thing to recognize is that every additional power that we raise it to is going to add an x, a y, or a z to each of the terms. And so what we're left with is a sum of all the possible permutations of x times y times z, such that the power that they're raised to, the sum of that is equal to n. So if we look at that very quickly, just to kind of do the first two steps of an inductive kind of proof in kind of an intuitive and informal way. If we looked at x plus y plus z squared, clearly we could just distribute this term across this, or either way, and what we're left with is x times x plus y plus z plus y times x plus y plus z plus z times x plus y plus z. So clearly x is added to, we multiply the previous term by x, and then we add the previous term times y, and then the previous term times z. Similarly, if we were raising it to the third power, we could rewrite x plus y plus z to the third as x plus y plus z times x plus y plus z squared, distribute again, and again we're going to have an x times the previous term, or the previous power, x plus y plus z squared, y times x plus y plus z squared, and z times the same. And by writing this out, I didn't continue to write it out because it gets a little bit long, but if we look at it here, we see that we have all the possible permutations of the letters x plus y plus z of length 2. Every possible way we could do it is here, and the second part to notice, obviously, is that some of them, xy, yx, are duplicated. So the real challenge, and where the multinomial theorem comes in, is figuring out for much higher powers, or for any power, how many terms are in fact duplicated. Well, since we know then that for all I, j, and k, there is in fact a term in the sum such that we have xi, y, j, and zk. The only question left is since there's a repetition, there may be some constant coefficient. It may come up 5 times or however many times. So the only question we have left to ask is, what is that coefficient? Well, it turns out that this is the exact same thing as saying, okay, we have a string of length n, because we could write this out as x times x, I times, and y times y times y, blah, 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 j times, and z times z, k times. And since I plus j plus k is equal to n, we have the length of n. And again, if we were to place, the x's, say there were two x's that were here, and we were to swap positions, it would have no impact. So obviously the x's are indistinguishable, so are the y's, and so are the z's. So what we expect to have is just the same exact counting technique that we used before. We start off, there are a total of n spots. We place the I k's, leaving us with n minus I. We place the j y terms, and we place the remaining k in that location. So what we're left with is, and what we expect is there to be n factorial over I factorial, j factorial, and k factorial. That would be our leading coefficient, which gives rise to the multinomial theorem, which states that instead of just worrying about x, y, and z, if we had any number, in this case there are m of them, but any number of terms in here raised to a power, in this case n, since we showed on the last slide that expanding this is indeed going to give us every possible combination, every possible combination of x to the n1, n2, nm, and that's exactly what this here stands for, over all the possible ways of having n1, n2, and nm, such that their sum is equal to n. In other words, just like we said, I plus j plus k is equal to n in this case. The sum of all of these coefficients is equal to n. Then the leading coefficient is just going to be the total, n factorial, over n1 factorial, i.e. the number of indistinguishable x1s, times n2 factorial, i.e. the number of indistinguishable x2s, and so on, all the way up to the number of indistinguishable xm terms. So the multinomial theorem, again, although seemingly dissimilar, is actually taking advantage of this whole concept of strings or boxes, or however you want to think about it, to figure out its coefficient, and is actually integral in figuring out this fundamental theorem in mathematics. Alright, so to wrap it up, let's look at one quick example of this. So if we were to expand our multinomial, w plus x plus y plus z to the 8th, what would be the coefficient of this term here? W squared plus x, w squared times x cubed times y times z squared. Well, again, we can think about it as tossing unlabeled balls, i.e. indistinguishable. This isn't x1, x2, x3, they're just x. Throwing them into 8 bins, or creating strings out of these x's, y's, or w's, x's, y's, and z's, rather, of length 8. So in this case, we're going to do the bins, since since it's my default is to use strings. I've been using that probably more than I should. So let's start off by placing the w's, for example. Let's start off by placing y. There are 8 choose 1, or 8 ways of doing that. Then let's place the z's. Well, there's 7 spots left, so if we were to place the z here and a z there, that would work. If we were to place the w's, there would be 5 spots left, and 2 of them, so 5 choose 2. And out of the remaining 3 spots, obviously it's going to 3 choose 3 is 1, but that would be our final move. Now, again, recognize that this, if we think about it really as this times this times this times this and so on, I'm going to get rid of that to make it a little bit less sloppy, this times that, times that, times that, and all the way down the line, we would in fact have w squared, x cubed, y, and z squared. And so we see again that this abstraction in fact represents something very concrete. And so the other thing to note here is that the order of choosing the things doesn't matter, so long as you place all of the y's at once, all of the z's, all of the w's, and all of the x's. Because what we'll see here, if I can clean this up here, is that our coefficient is, in fact, even though we did it in a different order, and we look at it here, we actually end up with exactly what we expected: 8 factorial over 1 factorial, the number of y's, 2 factorial, the number of z's, 2 factorial, the number of w's, and 3 factorial, the number of x's. So again, it's just as we expected from the multinomial theorem. So in conclusion, when dealing with permutations of indistinguishable objects, the most important thing to be able to do is abstract the problem. The first step in that, obviously, is noticing that some of the objects are indistinguishable. For example, in exercise 2, where you were figuring out the path from the origin to some point, recognizing that the x's, even though this move going from here to here is different than that move going from here to here, that in fact those x's are indeed indistinguishable. Wrapping your head around that concept is important. Second is, whether you're dealing with balls and bins or strings with characters or however you want to think about it, it's really important to come up with an intuitive visualization of the mechanisms that are at hand. We have a formula right here, but the important part, again, when I've beaten it over the head, I'm sure, is to understand where it comes from. Whether it's choosing the locations, starting with n, choosing k places, then having n minus k places, etc., or thinking about it in terms of the green and yellow objects and how the permutations total divided by the permutations of the other objects are indeed equivalent to our expression as well. Finally, again, the multinomial theorem is a very important application of this concept, and it's very important to recognize that finding the coefficient is the exact same thing as counting fruit or the paths. And again, that harps on the whole notion of the abstraction and why it's so important. So I hope that this video helped you guys understand the whole concept of permutations and indistinguishable objects a little bit better. Visit our website at knowatom.com. That's KNO atom, ATOM.com, for more videos on discrete mathematics. And have a good day, and thanks for listening.